So far, we looked at naturally aspirated engines, where the induction taking place due to the vacuum created inside the cylinder as the piston comes down from its top dead center during the intake stroke. But I'm sure all of you know that there are devices fitted into the intake system in certain engines where you could forcefully induce air into the cylinder. So that is what we are going to discuss under this topic, supercharging and turbocharging. Now, we all know that the power produced by an engine equals to the mass flow rate of fuel multiplied by the calorific value and the thermal efficiency of the engine. Accordingly, the torque produced by engine is also directly proportional to the mass flow rate of fuel. And then the mass flow rate of fuel is again, we can work out considering the air-fuel ratio of the engine at a given instant. Accordingly, mass flow rate depends on the air-fuel ratio, the density of incoming air, and the volumetric efficiency, of course, and the displaced volumes, engine speed, and so forth. Now, one way of increasing the power, you can understand. Now, we all know that the power produced by an engine equals to the mass flow rate of fuel into the calorific value multiplied by the thermal efficiency of the engine. And we know that the torque equals power into speed. Accordingly, the torque is also directly proportional to the mass flow rate of fuel. And then mass flow rate of fuel, we can work out considering the volumetric efficiency, air-fuel ratio, the density of the incoming air, and of course, the displaced volume of the engine. And as you can see here, if you run an engine with a fixed air-fuel ratio, then mass flow rate of fuel could be increased if you increase the density of the incoming air. So that is one way of increasing the mass flow rate. On the other hand, you can do the same thing by increasing the size of the engine, that is displaced volume. And accordingly, we can see, as we understood earlier also, the fuel burned by an IC engine is limited by the amount of air that you sucked into the system during the intake stroke. So usually the air-fuel ratio in gasoline engines is more or less fixed at stoichiometric. So more the air you sucked in, more fuel can be burnt and more power could be produced. So in order to boost the power produced by an engine, we could think of two possible ways, as I just mentioned. One is making the engine larger, that is increasing the swept volume or the displaced volume. And on the other hand, we could increase the density of incoming air. So the focus in this particular discussion is more or less on the way of increasing the density of incoming air so that we could burn more fuel and produce more power. So the devices that we use for this increase in the density of air coming in is the turbochargers or a supercharger. Now, if you concentrate more on supercharging at the beginning, so that is a method of increasing air capacity of an engine. The device that we use to do that is more or less known as the supercharger, which is merely a blower or compressor that provides a dense charge into the engine. So as I said earlier, more fuel could be burned if you increase the density, because the air-fuel ratio calculated based on the mass, not the volume. So there are three basic methods of supercharging. One is mechanical supercharger, where you connect a compressor directly to a crankshaft attached to the intake system. so that you can suck air into the cylinder. And then the turbocharging, it's more or less the same thing, but the compressor is not connected directly to the engine crankshaft, but the compressor is driven by the exhaust gases. And then the third type is the pressure wave superchargers. Mostly, this type of superchargers make use of tuning effect to boost the charge. Now, the supercharging is not a modern concept that was invented long time ago in 1878 by Douglas Clark. And then the supercharger for IC engines were developed by Delmer in about 1885. And then the first supercharger is used in internal combustion engines or automobile engines by Mercedes-Benz in 1921. There are two main types of compressors used for this supercharging. One is positive displacement compressors, where we could expect a constant level of pressure increase at all engine speeds. Other type is dynamic compressors, where the delivery pressure increases with the increasing speed. And this type of compressors, they accelerate air into very high speeds and send it through diffusers so that it slows down and the pressure increases. So there are two broad types of compressors, dynamic compressors and positive displacement compressors. In positive displacement compressors, gas is compressed by the movement of a compressor boundary elements. And on the other hand, in the dynamic compressors, the rotating element at the tangential velocity to the flow, which is converted to pressure in a diffuser. So there are two types of positive displacement compressors, rotary compressors and reciprocating compressors. And in fact, there are three types of rotary compressors which are tried out in internal combustion engines as superchargers. The Roots compressor, the first generation, the screw compressor, as well as the vane compressors. The reciprocating compressors are hardly used in internal combustion engines, but for other air compressors, the reciprocating compressors are used. You have a piston cylinder device as the operating mechanism. And there are two types of dynamic compressors, the radial and axial compressors. And in internal combustion engines, mostly the most common type is the radial compressors, but the axial compressors are used in gas turbines. The oldest design is the Roots compressor. The problem with this Roots compressor is it's bulkier, so that its weight is too large, and at the same time the efficiency is around 50%. And as a result of that, the people invented these screw type compressors, where there is a conical tapered rod compressors there inside the rotating house. This is more efficient than the Roots compressor, but the drawback of this design is it's very expensive. Accordingly, the most popular type of compressor that is used frequently in internal combustion engines is the centrifugal supercharger, which is more efficient, and you can make it smaller in size, lightweight, so that its efficiency also could be increased. And the centrifugal compressors or the superchargers, as a result of its lightweight and small size design, could boost the pressure quickly. And as I said earlier, their boosting is proportional to the speed. Therefore, at low speeds, the boosting is fairly small, but at large speeds, you could expect greater boosting, that is greater pressure ratio. So this is a real picture of centrifugal supercharger. And this is a centrifugal supercharger fitted into an engine. This is the intake system, and supercharger, and the air is delivered to cylinders from this side. Air is induced from this side. And this is a cutaway section of centrifugal type supercharger. So there is a gear arrangement inside. The gear ratio is around 30. That means if an engine runs at 2000 RPM, then that speed is multiplied by 30 times at the supercharger, and at the impeller rotates around 30 times more than 2000 RPM. So that means about 60,000 RPM. Achieves fairly large speeds, so that high pressure boosting could be expected. And on the other hand, the turbocharging is more or less, as I mentioned earlier, it's again the same type of centrifugal compressor used, but the compressor is not driven by the engine crankshaft, but by a turbine, which is connected to the exhaust system. So the exhaust gas temperature and pressure provides necessary energy to turn this turbocharger, a turbine, and the turbine is directly coupled to the compressor. And the compressor is more or less the same type of compressor that we discussed earlier. So this is a cutaway section of a turbocharger. So this is the turbine, this is the compressor. The hot air or the exhaust air comes in and goes out to the exhaust pipeline from this side. And the inlet gas comes in, air comes in from this side, and boosted air goes out from this side. Now, in the case of supercharging, the main objective of turbocharging is also the same, just to increase the volumetric efficiency. But only difference is, as we looked at earlier, in turbocharging, the compressor is driven by the exhaust gas. So the temperature and the kinetic energy in the outgoing exhaust gases, as well as the pressure energy, would use as a source to drive the turbine. So usually these turbines run at speeds of like 100,000 to 150,000 revolutions a minute. Now, one observation that we can make with this turbocharging or supercharging is when you boost the pressure or increase the pressure, then the temperature also increases. That lead to reduce the density of the incoming charge. And there are advantages of disadvantages of that. If you look at the spark ignition engines, this becomes in a way a disadvantage, because the higher temperature at the beginning of the combustion would lead to auto ignition of N gases, and that phenomena is known as knocking that we looked at earlier. And on the other hand, generally, increase of temperature would reduce the density, and again, that will offset the expected boosting. And at the same time, increase of temperature would lead to increase of NOx emissions, and at the same time, increase of temperature at the beginning of combustion would support the combustion process. Particularly, it will reduce the ignition delay and improve the combustion efficiency. Accordingly, there has to be certain degree of addressing the issues or the disadvantages of this increase of temperature and reduction of density. One way of doing it is aftercooling or intercooling. So intercooling helps us to cool down the intake air again back to a certain temperature, which will enable the increase of the density, reduction of the tendency for NOx emissions, as well as knocking in spark ignition engines. And another device that we find is in turbocharging is a wastegate, which is mostly a bypass valve. And traditionally, this wastegate is controlled by the pressure of the intake air, and certain degree of bypassing of exhaust gases could take place as a result of this operation of the wastegate. So now in the modern engines, in other words, this wastegate is not controlled by the incoming air or inlet air pressure, but instead there are electronically controlled valves, so that microprocessor based control systems could be enabled with such valves. So engine management unit decides when to operate this wastegate, and accordingly, we could control the amount of turbocharging required in the engines. So in certain modern engines, in certain low speed and low load operating conditions, the turbocharger is shut down, particularly petrol engines. And whenever the engine boosting is required for the acceleration and running at high speeds and pulling large loads, the wastegate is controlled such that the turbo boosting is enabled and required power could be produced. Now, this is the diagram of intercooling system. So the turbocharger, compressor, and the compressed air goes through this air cooler, and it enters the engine at a lower temperature than the outlet temperature at the compressor. So it can be air-to-air heat exchanger, or it can be air-to-liquid heat exchanger. Usually, it is air-to-heat heat exchanger, and this diagram shows a real picture of a intercooler turbo system. This is the radiator, which enables cooling of air. Now, these turbochargers and superchargers are used in engines in several different configurations. Now, for example, the simplest one, the mechanical supercharging configuration, where the compressor is driven by the crankshaft. So this is more or less a mechanical blower. And the turbocharger that we looked at, the compressor is driven by the exhaust gas of the engine. So that is basically normal turbocharging that we looked at. And there can be engine-driven compressor and turbocharging. There are two compressors in this case. Certain degree of compression is done using engine-driven system, and then it's further compressed using a turbocharging system. So this is the configuration of engine-driven compressor and turbocharger. So it is a supercharger and turbocharger together. And then there are two-stage turbocharging, where you have two compressors and two turbines cascaded, as you can see here. So it's two-stage process for better boosting. And then there's another one, turbocharging with turbo compounding, where you have two turbines. One turbine is driven by the engine out, engine crankshaft, and the other turbine is driven by the traditional turbo unit using exhaust gases. So you can boost the operation of turbine by having two turbines like this, and better compression at the compressor could be expected. And this is the configuration of turbocharger with intercooler. So after the compression, the gases or the air is sent through an intercooler that we looked at earlier, so that the reduction of temperature and increase of density could be expected. Now, as I mentioned in my previous slide, so the superchargers or turbochargers in SI engines is quite of a challenge, because if you increase temperature at the beginning of the compression or combustion process for that matter, then definitely the tendency for knocking would be increased. However, with this intercooling, as we know, that tendency could be reduced to a great extent, and also certain supercharged or turbocharged spark ignition engines operate at a lower compression ratio. Therefore, you could reduce the tendency for knocking. At the same time, so these turbocharged spark ignition engines were not that popular until recently, but with the modern technology of electronically controlled valves and improvement in intercooling systems and so forth, we can now find turbocharged SI engines in commercial vehicles. Turbocharging was initially used in compression ignition engines traditionally, and the compression ignition engines, there is no issue with auto ignition. So anyway, it is an auto ignition process. Therefore, you can have higher temperatures at the beginning of the compression as well as combustion. So that would improve the combustion process, reduce the ignition delay, and reduce the combustion duration, and improve the efficiency of combustion process. Therefore, the turbocharging or supercharging is quite popular among compression ignition engines. And one of the issues with turbocharging is the turbo lag. Turbo lag is more or less the delay in response. Now, these turbochargers or superchargers, they are made using mechanical elements. Therefore, there is a certain degree of inertia within the system. And due to that, the system has a certain time constant or delay in responses. So that delay in responding to the driver input is called the turbo lag. So the driver presses the accelerator pedal and requests more and more power to be produced. But if the turbocharger could not respond that quickly, then there is a delay in driver's request, delay in accommodating the driver's request. So in simple terms, this is a diagram downloaded from the web. So this diagram clearly shows what this turbo lag is. Now this rope is longer, so even though you hit the hose will start running as soon as whatever the stone hits him. But due to this extra length of the rope, this person has to wait for a short time until he is dragged by the hose. So this is what is meant by the lag. Now, with the modern manufacturing technologies and so forth, the compressors and the turbo units were made using highly low weight material, reducing moment of inertia of the rotating parts and the weight of rotating parts. And accordingly, the turbo lag also was reduced significantly in the modern day technology. Now, if you look at the thermodynamic aspects of this supercharging and turbocharging, just to get an understanding about what exactly happens in terms of thermodynamics properties, just let's consider a compressor, a simple compressor like this. State 1 is intake, state 2 is exit of the compressor, and the compressor need to be run by an external source. So some work need to be done on it, and the mass flow rate of air is in a dot. Now, if you define the compressor efficiency, neta C, that is the rate of change of ideal work divided by rate of change of actual work. Now, in the compression, always the actual work required to run the compressor is more than the ideal amount of work that is required due to the frictional effects and other things. And if you look at the TS diagram, now this is the intake to the compression, and this line represents the pressure at the outlet of the compression. So this is the pressure boost rather. So we want to increase the pressure from P1 to P2. And if you consider an ideal process where there is no heat transfer, so isentropic process, so there is no change of entropy. So you can go from state 1 to state, let's say 2 prime. Now, the physical process is not isentropic. So there is a certain degree of heat transfer. Accordingly, actual process would be not an isentropic process. So there is a change of entropy when you are boosting pressure from 1 to 2. Now, considering this phenomena, if you write down a small equation for ideal work per unit time, we know that the work per unit time is the change of enthalpy, rate of change of enthalpy, I would say. Then this ideal work would be mass flow rate into Cp into the difference of the temperature from the initial state to ideal process. In this case, it is 2 prime. So if I take T1 out, then what I would get is the same thing, T1 M dot A Cp T1 into T2 prime divided by T1 minus 1. And since this is an isentropic process, we are talking about ideal process, then we can relate the temperature ratio to the pressure ratio using isentropic exponent like this. So we can replace this temperature ratio using pressure ratio. And if you divide this by the compressor efficiency, then you can find out the actual work per unit time. So actual work per unit time or actual power is 1 upon eta C, that is the compressor efficiency, MA dot Cp T1 into P2 over P1, gamma minus 1 over gamma to power minus 1. So we can find out what could be the actual power required or work per unit time is required if you know the compressor efficiency. Now also from thermodynamics point of view, we know that actual work per unit time or actual power is MA dot Cp into T2 minus T1, T2 minus T1. Accordingly, if you know the actual one from ideal analysis with the help of compressor efficiency, then we will be able to find out what the value of T2 is, the real value of temperature increase, T1 plus actual power divided by MA dot into Cp. So this gives you the temperature increase due to the compression. On the other hand, if you look at the turbine side, the turbine is supposed to give work out from the turbine to run the compressor. So number 3 is the exhaust gas intake into the turbine, and number 4 is exhaust gas out of the turbine. And the turbine work is W. So work per unit time is W dot, which is the power. So if I define my turbine efficiency in the form of actual power divided by the ideal power. So in this case, this is the opposite action to the compression, where the compressor, we have to give work to drive the compressor. Now the turbine gives out some work out as a result of this turbine effect. So always the ideal situation has a better performance than actual situation in the case of turbine. It's other way around in the compressors. Now, if you look at the TS diagram again, now in this case, the pressure would reduce as the turbine rotates. Some of the energy is absorbed, pressure energy and the kinetic energy of the incoming air or exhaust gases would be converted into work, so the pressure would be reduced. So initially, this is the pressure at state 3, that is intake to the turbine, and this is the pressure at state 4, exit of the turbine. If you assume this ideal situation, that is isentropic situation, we could expect pressure to be dropped as an isentropic process without change in the entropy of the system. That is indicated here as 4 prime. But real system, there is no isentropic situation. Therefore, actual system is not an isentropic process. So there is a certain degree of change of entropy. And that is indicated as number 4 on this diagram. Now, as before, we can initially concentrate on this ideal process. So ideal power generated by the turbine would be M dot Cp into the temperature difference between ideal situation, initial and exit at the ideal conditions. And now if you take out T3 from this equation, then you get this temperature ratio here. And we are talking about isentropic process. Therefore, this temperature could be related to the pressure ratio, as we looked at earlier. And you can simply substitute this T4 prime divided by T3 with this pressure ratio into gamma minus 1 divided by gamma power. So, with the help of the turbine efficiency, actual work work per unit time is turbine efficiency into ideal work per unit time. So ideal work per unit time we know now. Accordingly, we'll be able to find the actual work per unit time produced by the turbine. And similarly, we know that the actual work per unit time produced by the turbine is m dot Cp into T3 minus T4. That is the actual process. Accordingly, if you know this actual work per unit time in terms of ideal process as well as the thermal turbine efficiency, then you will be able to find out the temperature drop as a result of this taking work out from the outgoing exhaust gases. And the performance of aftercooler or the intercooler is also directly related to the temperature drop or temperature reduction, and it is defined as in the form of cooler effectiveness, which is defined as the ratio of the measured temperature drop to the maximum possible temperature drop that would bring the cool fluid to the coolant temperature. So maximum possible temperature drop that would bring the cooled liquid to the coolant temperature. So the temperature drop across the cooler, the entrance and the exit of the cooler is T1 minus T2 as defined here. And the maximum possible temperature drop that would bring the cooled fluid to the coolant temperature is T1 entrance stagnation temperature minus TW coolant entrance temperature. Usually, this coolant effectiveness is in the range of 0.6 to 0.8 or 60% to 80% in usual aftercoolers. And there can be 2 to 3% pressure drop could be expected across the aftercooler. But for this kind of analysis, we could neglect that. Now, this graph shows us the effectiveness of this aftercooling. If it is not, in this case, if you consider, for example, operating pressure ratio of 1.8, if it is uncooled, you could say the density ratio 1.4. And if it is fully cooled, 100% cooled, you could say density ratio 1.8. So the density could be increased through this cooling. So we will not be able to achieve full cooling, but usually, as I said earlier, it could be up to 0.8, in between 0.8 to 0.6. Therefore, this density ratio could be increased from 1.4 to 1.6 or 1.73, for example. So we could boost the density ratio in that range using aftercooling. Usually, the peak pressure ratio in a compressor is around 2.5, and the amount of breaking mean effective pressure consumed by the compressor is up to 24 bar, and the performance of compressor is limited by the compressor aerodynamics, cylinder peak pressure, as well as the NOx emissions. Now, if you look at the turbine and compressor characteristics, usually the pressure, the delivered pressure, the output pressure is a function of many parameters like mass flow rate, universal gas constant, temperature, pressure, speed, the diameter, viscosity, specific heat ratio, and geometric ratios. So it's quite normal in this kind of analysis to look at these pressure ratios in terms of non-dimensional quantities. So we could say with the non-dimensional analysis, I'm not going to go into details about this, but I'm sure you all learned about these things under fluid mechanics. We could represent these quantities in a non-dimensional form. This is velocity, this is density, This is again velocity. And we all know that if the Reynolds number is very high, then the dependence on the Reynolds number of the flow is weak. And then if the geometry is fixed, that is mostly in the compressors that we use in internal combustion engines, the diameter of the compressor blades or impellers would be the same. Accordingly, for fixed geometry turbo machinery, we could say pressure ratio is a function of N divided by square root of T1 and M dot into square root of T1 divided by P1. So this is in a way kind of a standardizing the operating or the test conditions of compressors and turbochargers, where you normalize your measurements of mass flow rate, pressure ratio, speed to standard temperature and pressure. So irrespective of what temperatures and pressures that you make the measurements, these quantities would give you normalized values. Now, before moving on to compressor characteristic maps, a couple of more things if you take into account. The surge, the compressor surge is basically when the inlet flow rate is reduced to a greater extent such that the head developed by the compressor is insufficient to overcome the pressure at the discharge of the compressor. We call the surge occurs. So when the surge occurs, the output pressure of the compressor drastically is reduced, resulting flow. We could expect some kind of flow reversal even as a result of surge. And the stall is a kind of a non-uniform flow distribution across the blades. As a result of that, then there can be stalling. And basically, the stalling happens at a very high load conditions or if the blades are heavily loaded. Now, this is the compressor map that gives us, that is in fact a variation of efficiency as well as speed under different flow rates and pressure ratios. So these are corrected pressure ratios and corrected speeds, as we have seen here in the previous slide. So corrected to the non-dimensional quantities, as you can see here. So these quantities are given here and here. So these are the speed curves. So the testing under different speeds. And these are the dotted curves are, or dashed curves are the efficiencies. So with this kind of map, we could find for a given pressure ratio of operation, for example, if you say 2.5, and for a given mass flow rate, what should be the speed of operation to give us the maximum efficiency could be found using these kind of compressor maps. And in this one is a turbine map where the y-axis is turbine mass flow, again normalized quantities, and then the turbine pressure ratio. And these curves are the efficiency curves at different speeds. So these are the corrected turbine speed divided by 1000. And these are the mass flow rates. So for a given pressure ratio, so we could find what should be the best speed as far as the efficiency is concerned, as well as what should be the mass flow rate or the corrected mass flow rate through the turbine. So this is just a pictorial representation of a turbocharger. So so usually when it comes to design or selection of compressor turbine units for turbocharging, we need to do an exercise called compressor turbine matching. So the objective of such compressor turbine matching is to find the operating point of the turbine, what should be the mass flow rate, what should be the fuel flow rate, turbo shaft revolution, and compressor and turbine pressure ratios. And these things are found based on the brake power output of the engine speed, compression and turbine map, and engine maps. And the procedure of matching is given here. I'm not going to go into details one by one. So we will look at this procedure through an example of a tutorial exercise later on. So these are the references that you could go through if you want to study a little further on this.